I think everyone agrees we're going to need landing pads, launch
Mm-hmm.
pads, berms for protection, for shielding. Berms are going to be, being able to build a berm is, it seems so simple. You're just like, you're just pushing a bunch of dirt into a mound. Like we do that all the time. But because of the gravity, because of the lack of cohesion, because of the lack of, humidity to, like, keep these things solid, it's not that easy. You push this stuff around and it just blows a little bit
Slides
that way.
off. Yeah.
It's more like dunes that can just very easily shapeshift and morph. They don't have any real, structural integrity. So that's going to take some serious engineering still, development. So, and we're actually working on that specifically, potentially with some new challenges coming up from NASA, and some things that next time when we get together, I'll be able to talk about a little bit more, most likely. But so landing pads and berms, are kind of the key ones, and then really just being able to create dust-free zones, to protect equipment, to make for repeat access, not just of the lander in a particular spot, but to get your rovers and your even your astronauts, and to get your equipments and your processing set up in areas that is already sort of, dust controlled. Those are going to be, from our vantage point that we've assessed so far, those are going to be really the initial infrastructure elements. The habitats, I think, are going to be much further beyond that, because initial habitats will most likely be, pressurized spacecraft that are landed and just kind of, dedicated to that. I mean, we don't need to, we can, just like they built ISS, we can build some very, very elaborate, comfortable, I don't know if they'd call them luxurious or comfortable, but, they're designing habitats already that can just be basically landed. And when you get to these larger scale landers, like what Blue Moon is, or like Blue Origin is building with Blue Moon, and some of the bigger companies, then, modules for those big habitats will most likely be delivered for the foreseeable future, as opposed to built in place.
Okay, yeah, because digging ain't easy. You've got the regolith, and then there's a foundational layer underneath there that's quite a bit different, and you've got to figure that out.
Simulating all of that is really tricky. So we've got our work cut out for us to try to do as much testing of that kind of stuff here on the ground, and then start doing some technology demonstrations hopefully in the next 5 years or so, 4 or 5 years.
Let's talk about ISRU for a little bit. I'm going to link to a NASA page, I think that you shared with me a while back on it, down below in the description, but let's assume that the audience knows nothing. What is ISRU, and what are you doing involved with it?
Okay, so ISRU is in situ resource utilization. It means using the resources that are in place. That's the literal definition. I call it building off the land, or I've heard other people call it that. So I think that that's a nice way to put it. Our program, under our research program, we call it dust to structures. And it's that kind of, I think paints the picture really well of just going in and just using the raw material that you have in front of you, and bringing as little with you as possible to turn that into structures. So it could mean, here, like I said, 3D printing with clay, 3D printing with sand, as one of your major aggregate components. And then, of course, in the case of Lunar, working with the regolith.
All right. Are there any specific research areas?
I want to say so I want to qualify all that and say I'm actually obviously looking at this through a construction lens. ISRU is actually much broader from, in terms of the way that NASA uses it, because we're also talking about how we use the water, for life support, for drinking, for radiation shielding, for breaking it down into propellant, which is the primary thing that we're trying to use it for. It's the whole reason all this stuff is happening, is because water will turn into liquid oxygen and hydrogen propellant. So that is ISRU. Oxygen extraction from the regolith. There's a lot of oxygen in the regolith tied up in oxides. So you can do electrolysis to release the oxygen and create a, you know, for breathing, as well as again for fuels. And so that's ISRU. You can also get metals, titanium, other material, other minerals like silica and aluminum, and not a lot of calcium, a little bit, but primarily I think titanium and silica, and that can be used for, you know, as building more sort of material, you know, components or metals for material fabrication. So that's all ISRU. I don't know that there's a case right now because of the way how much extraction energy it would take to do the extraction on those. There is a case for doing regolith consolidation for infrastructure. I don't know if there's actually a case for doing like metals extraction for building things out of metal, but that would technically be ISRU as well.
More engineers are not going to solve your problem. It's not a technical problem in that sense. It's a process problem. And the time to fix your processes was 20 months ago, and the second best time is today. This is Jason Kanigan, the president of Cold Star Technologies and the host of this podcast, the Cold Star Project, which is all about identifying and solving process problems for space companies, because that's what we do. And you can hear the entirety of this episode by following the link in the comment below.